Bonjour madame et messieurs, et bienvenue à ma discussion à propos So this is probably not 50% French, but it's like 1% French, and that won't be enough because my French is terrible. Sorry about that. Hello, about this talk, and today I'm going to talk about OptimusPrimeT, and all of you know that transformers, so we're going to talk about transformers, but not that kind of transformers. We're talking about monad transformers. Well, not that kind of monads, but you're not going to need a math degree today. It's actually going to be very simple. So I'm not going to confuse you with these kind of diagrams. A simple problem with these diagrams is that I don't understand them. So I can't explain anything about that. So if you're looking for a math lecture, I'm the wrong person today. So what we are going to talk about is monad transformers. So we take effects from one monad and put them into another monad so that they simply compose. So while writing this talk, I thought like, okay, I have to motivate monad transformers somehow, and yeah, I kind of have to explain monads for that. And so the problem is what I'm going to discuss in the next couple of minutes is that monads just do not compose like many other concepts like functors and applicatives. So I figured, okay, so there's a difference between monads and functors and applicatives. So I need to explain this difference first. So I think in the first 15 minutes of this talk, I'm not going to mention monad transformers at all, but we are going to start from the beginnings. We're going to start from functors. So everyone knows monads, right? So I mean, you've been to the last talk, maybe, but like monads are a nice concept, but there's a lot more to know behind them. There's a lot of theory and also a lot of practice which you can use for your day-to-day programming. So monads have a lot of use cases. So we have seen error handling with either in Scala set, and we also have parser combinators. I'm not sure how many people of you have used parser combinators. That's quite nice, actually. So many of the parser combination frameworks, for example, also the parser combinators in Scala, they are actually monadic. So you can just compose your parsers you can just compose your parsers and have a natural expression style, and you can even use it in for comprehensions if you want. Also, value-oriented parallelism, what do they mean by that? Basically futures. So you have a type constructor which says, I have a value of type A sometime in the future, and they can be computed in parallel or whatever, and all you're talking about is the actual value, so you're not dealing with any of these underlying primitives, whatever they might be, however they might be implemented. And so monads have a lot of use cases in practical code. But code using monads has both mathematical and practical limitations. So let's have a look, first look. I've prepared a short demo code for that. We're first looking at this string to int function. And this function should be easy enough to understand. It returns the validation, NEL. The NEL stands for non-empty list. You can ignore that bit for now. Basically, it says this function can return either a success, so if the parsing of the string to int succeeded, and if not, if it catches the number format exception and gives you back a failure, and the failure is just list with just one element. Please don't care about that. It's actually a list, it's not just a single element. It's just an implementation. So let's try that code. All right. So let's say we have two inputs, and we want to parse them and then compute their sum. So as good programmers, we do that using validation, and we put that into a for comprehension. So let's see. Okay, we get a success. We actually got 3 out of there. And that's nice. But we also have failing cases. So what if I change one of these numbers to be a failure? So for example, b, which cannot be parsed as integer. So the for comprehension gives me back a failure and gives me the invalid number b. That's nice and all, but what happens if I also change this year's? So I have two invalid numbers. And if I execute that, I get the failure for A, but the failure for B completely disappeared. So that's not really nice, isn't it? So what we usually want when you're using validation from Scala is we want to accumulate all the errors which appear. Imagine you're using a website, you have to fill in a form, and then you have like name and surname and address and something like that, and you submit that form and you did something wrong, and the website tells you, okay, your address is wrong. You correct the address and you submit again and says, oh, your postcode is wrong. I mean, websites do that, but we don't want that. We want all the failures accumulated so we can tell the user them all together. So there's this funny operator, pipe at pipe, which is sometimes called a Hupel load operator, and we're trying to use it, and let's see what happens. Okay, so please ignore this completely weird type. This is also an implementation detail. So what it means basically is that Scala Z tries very hard to convince the Scala compiler that it's actually type checked. And you can see here we get both the failures. So this is a for yield which internally uses the flat map method of validation, so it uses it as a monad. And this one uses it as so-called applicative, and in this case it's able to accumulate errors. And I'll try to explain why. So let's start from the beginning. So Funktor in German means radio control gate. It's a nice pun for all the German speakers here. So what is a functor? A functor is something which describes the transformation of data. So if you have a list and you apply the map function, you transform all the pieces of data which is in that list. And you can have a lot of functors, so many things have data in them. So for example, option, and also future. So if you write that, you don't get 2 back, but you get some future which can be run, and then you get, if you run it, you get 2. As already described in previous talks, Scala Z has a generalization of that pattern. And it says like, this is something which contains data, and you can transform it from one piece of data to the other piece of data. And I don't really like the analogy of saying a functor is a container because, frankly, a future, for example, is not really a container. It describes a piece of data. It is not necessarily there already, so I don't really feel comfortable calling it container. Anyway, so it's just think about it, pieces of data. So what if we try more power? Also from the previous talk, applicatives. Applicatives are functors which give you one additional bit of magic, namely that you can transform independent pieces of data. So you can get a map function which takes more than one data argument. For example, you can take 2 lists and tuple them together and you get the Cartesian product. So this operation should be familiar to most of you, a Cartesian product. And again, Scala has a generalization of that. And you can imagine that as a map function on steroids. So you can have F of 2 independent pieces of data. You see, this B does not depend on A and vice versa. But you still can take a function which takes an A and a B, produces a C, and apply that to these somehow in parallel or as a Cartesian product, or what it does depends on the concrete applicative. This is not really the full story because, I mean, map 2 is sufficient to define an applicative, but you can, from that you can derive map 3, map 4, map 5, and so on. So you can really have an arbitrary number of pieces of data. So let's add even more power to that stack. Now we have monads. And monads are about transforming dependent pieces of data, right? So applicatives are about independent data. For example, if you have form validation, all your fields are already known. They do not depend on each other. So you can check each field in your form right after the other. You can also check it in parallel or whatever if you need to do a database lookup. The applicative just doesn't care, it's independent, so the applicative can do that. On the other hand, if we have some sort of sequence of actions, like if we have to compose several API calls or call to a database, for example, let's see, we have, assume you have an API which gives the user the ability to request a file. And it returns a future of int, where int is the number of bytes which have been written to the user. You have to do these things in sequence. For example, you first have to check that the user actually has access. So you need to call to the DB, get the access token of the user, get this token back. Then you can take this token, put it in the DB again, and then read the file which has been specified as input. Then you get the input, and then you first need to send the HTTP error that is actually okay, so the user has access and stuff. And then you can send the body, and from that result you can give that. So there's no way you can do these things in parallel, because it is a strict sequence. So you can't, even if you're using features and say like, oh, I have parallelism here, you can't, because these pieces of data are really dependent. And you can't do that with an applicative. An applicative requires you to have independent pieces of data. So also the formalization of Scala set here. We have a monad, and this has the well-known flattener function, and you can see here, if you look back, if you look at the signature of applicative and functor, you see that this transformation function is a signal A to a single B. But here you see it is already wrapped into an F. So really this is the dependent bit of that. You look into the values which are somehow described by this functor or monad or whatever, or container or whatever you want to call it, and then depending on what is in there, you create a new one. This is also true, for example, for these parser communicators, which I said are monads. So you can have a grammar which says, in my first column, I have some data type or whatever, some type specification, and then depending on that type, I have another parser for my second column. So this is really, monads are about dependent pieces of data. And interestingly enough, even though I haven't written it here, monad extends applicative, and we can implement the applicative operations by just having a monad, by just having flattener. The implementation is not very exciting, but it can be completely described by the type. So if you follow the type, there's just one possible implementation for that. And as you can see here, it's completely sequential. So you have to first flatmap, get the A out, and then get the B out, and then you can apply here. So a monad really forces you to be sequential. Okay, time for another demo. So, in my first demo, I've shown that if you use for yield with validation, you get silent discarding of error messages. This is not really a good thing, and it was using ScalaSet 7.0.6. And because this wasn't a good thing, we fixed it to ScalaSet 7.1, and I'm going to show you. So I'm just going to change the dependency here, just changing 706 to 710, and let's see what happens. All right. So if you try the very same query again, you'll actually get a compile error, because now in ScalaSet 7.1 you can't use validation as a monad anymore, because it silently discards error messages, and we don't want silent discarding. On the other hand, the applicative composition can still be used. So you can still use that operator and get all your figures back. And what's even more interesting is that using applicative, you get a lot of very powerful combinators. So people usually say that if you're using monads, you can have access to all sorts of libraries, which just operate on the fact that something is a monad. But that's only like one half of the story, because lots of these libraries can also be written by just knowing that it's an applicative, so you don't actually need all that full power. Here's another example. Let's say you have a list of things and want to convert it, all right, you have a list of strings. Let's say you want to parse all of them to integers. So I'm probably not going to explain what the traverse means, and not even going to explain what the U means in the traverse U. But let's just say this function goes through the whole list, looks at any value, pipes it into the string to in function, and then collects all the results. And if we have failures in here now, so for example B, then the whole thing fails, and we get all the error messages. So if I'm going to add another error here, we get all the errors combined. And this is really powerful, because now you have the capability of transforming a whole bunch of things together. And applicatives can do that because all the elements in your list are completely independent from each other. So you couldn't do that just like that with monads, because then you would again only get one error message. But since you have a list of things, all the things are already known, so there's no dependency. Alright, so any questions up until here about applicatives and monads? Alright, fair enough. So let's go on. We're talking about composition of functors now. So what is programming? Programming is abstracting. And non-composable abstractions are useless. So I think there was someone on Twitter like 1 or 2 years ago saying that you are not composable is the new you suck. So we're really talking about we really want to have composable abstractions, and as functional programmers we do that all the time. We just compose functions, and if you're using functors and stuff, we might want to compose them too. So what is actually a composition of two functors? Let's say we have this. Let's say we have another transformation function again, and we have a list of things, and now we want to transform the inner things in here, which is nested in these two levels of lists. So how would you do that? I mean, the trivial thing to do would be to write access as .map and then underscore .map again with this function. But as I already said, we want composability. So we don't want to repeat this map application twice. So we want to have something better here. So another demo. So what ScalaZ offers you is the ability to manipulate type class instances just by summoning them. So you can say, if I want to talk about functor of list, you can just write that down and you get the actual functor of list. And for example, you can let's give that name. Let's say val f equals functor of list. This is, by the way, an advantage of Scala over Haskell, because in Haskell you just can't do that like that. In Scala, we can actually get our hands on the concrete instances and manipulate them. So we can say, for example, here f.map, and so what's the type here? I'm just guessing. So I'll say 1, 2, 3, and then we want to add 1 to that. So you can just use these operations on the functor variable. And what's interesting is that functor, this f instance also has a compose method. So let's say f compose f. And now we have something extremely weird. Let me try to explain. This is a so-called type lambda. So what is this about? Basically what it says is that you have now a functor instance for something which is 2 levels nested. So you have varying alpha here, and if you map something, you don't map this thing, but you map the inner thing. Does that make kind of sense? Let's give it a name and try it out. Oh, okay. Right. Awesome. So we now were able to map 2 layers deep without actually calling map twice. It will all be handled by ScalaZ voice. And the good thing is, not only do the functors compose, but also applicatives compose. So we can also compose 2 completely different types of applicatives, and this is all really nice. So I'm going to give you another example here from real-world code. Let's say we have our strings again and want to convert them to integers, but we only want to do that if it's a positive integer in the end, so if it's a natural number. And if not, we don't want to get an error message, we just treat it as non-existent, so we want to give back none. So we want to map, we have a validation with an error message or an option of it. right? So we have 2 layers of validation logic in there. I have some code. So here's this string positive in function, and it looks almost the same in the same way as the other one. Just that we have an additional check, so if n is greater than 0, we give back the sum of n, and otherwise we say, okay, the parsing was successful, but it wasn't really the number we wanted to have, right? And we can see that in type, so we get back a validation of string or option in. So that's fun and games, but what if we actually want to do the same trick we did earlier with traversing a list of things and parsing all together at once? So I have to type some really weird code now. Please ignore that for a second. It's not meant to be written by hand, but I'm just writing it to make a point. Oh, actually, mistake. Sorry. Awesome. So now we have a combined applicative, and you can also already see here that we have some sort of thing going on, which kind of looks like what we want to have. We have validation, validation NEL with a string on the left side and an option of alpha on the right side. And now we can use that thing to traverse. So let's try the correct example for now. So nothing too exciting going on here because we have successfully transformed all the values, and both were positive, both were valid numbers, and they were also positive. So we get a success in sum. Now let's try what happens if we manipulate that. And we get back a success of none because we could parse all the values, but we couldn't actually, some of them were actually not positive. And it also has the same behavior as before, so if we have something which is not integer, we get the error messages. Right, so we get the behavior of the original applicative just fine, and we also get the additional effects of the option applicative. So this is really powerful because function applicatives allow us to compose stuff, and we don't have to do this nesting by hand. We can just write it once, and everything will continue to work like before. Okay, so I've told you now in great length that functors and applicatives compose, and by now you probably guess what's going to happen now. Surely we can also compose monads, except we can't. So if you try to write monad, option compose monad list, what you will get back is an applicative, not a monad. So that's really sad. But this only holds in general. Surely we can compose specific monads. The reason why this doesn't work is deeply mathematical, but I'm not going to talk about that. Let's rather move on. So now is the time I'm actually going to talk about monad transform. So what are our tools? We have a monad of F and a monad of G, and both have that method. And they both are identical except for this varying type constructor here, which I actually made wrong here, so this should be A to G of B and G of A and G of B. And our goal is to write the following function. We take an F of G of A and have an A from F to G to B and want to F of G of B back. And you can try to implement that function. It's really a nice exercise, and you will soon notice that you can't actually. If you try to go somewhere in here with the flat map and map you have, you see that you can maybe produce an F of G of F of G of B, but then you lack the structure to actually collapse that together. So you have now a mess of 4 layers of type constructors with no means of actually smashing them together. So in general, as I said, it's impossible. Quick computer science interlude. All of you probably know the halting problem, right? So it's impossible to write a REST API when post JavaScript program which tells that this JavaScript program terminates. This is in modern terminology. But we can try to defeat that halting problem. How? There are programming languages which only accept terminating programs. So how can these compilers actually do that? I mean, it's undecidable, but how can they? The reason is they approximate. So what they say is, I only accept a program for which I can be sure that it terminates. So they have some kind of heuristics. And if they see a program which is kind of contrived, which they don't really know, could it terminate or could it not, then they just reject it. It could terminate, but they don't know it, so they reject it. Programming languages which do that include Coq, and also we can do that in Idris and Agda and all these theorem prover kind of languages. And they can deal with that just fine. So it's not really defeated, it's just like reducing the problem to a special case. They say, for most of our cases, we can actually detect whether something terminates, and for all the other cases, well, they'll screw them. And it's the same thing we are going to do right now. We are going to compose particular monads. So let's say we still have our outer monad F with the flat map function, and then let's say, okay, we don't want this general flat map combined for f of g. What we say, we want a flat map specifically with an option in there. So we have f of option of b, not f of g of b, but f of option of b. And same here, so we also take an f of option a and f of option b, we get it back. So just quick show of hands, who of you thinks you could implement that function? Really? No one? Let's just follow the types. So here's the function we're trying to implement. And yeah, so how would we go on about doing that? We get this monad we get that monad as an implicit parameter, and now we need to do something with our input. And I'm going to do type-driven design here, TDD, which probably all of you do. And there's some niche programmers which call TDD test-driven design. I have no idea where they took that from, but I mean this T is clearly for types. So what we're doing is trial and error. We just type something in and see if the compiler accepts it, and if it doesn't, we look at the compile message and then adapt our code so that it works. And at no point in time we actually have any clue about what's going on, but we don't need to. So we tried a simple thing that could possibly not work, which is saying that, okay, let's just flat map our FOA with F. Okay, so that didn't work. But we get a nice error message. What it tells us is that we found a function from A to f of option B, which we got, and it required a function from option A to f of option B. So the return type is already correct. We only need to do something for the input. And what can we do when we get an option as an input? Louder?
Match.
Match, exactly. We can match on it. By the way, the mathematician calls that proof by case distinction. Is everybody familiar with this triple question mark operator? It's just a placeholder which has any kind. So yeah, so the compiler did actually take that. Okay, the compiler's happy with that. Awesome. So now we need to decide something, what happens with the none case. I mean, if we have nothing, we can't just give back nothing. So we can't just take an A out of thin air. So we have to give back nothing again. So there's a slight complication because we need to wrap that nothing in F, but we can do that. So Scala has this operator called pure, which takes a value and wraps it into a monad. Whee! It works, it compiles. So now we have 50% of the cases done. Now with the remaining 50% of the cases. So we have a sum of A now, and we can try to guess what this type is here, but we already knew it because the compiler already told us. So it's this takes option of A. So this thing here probably has type A, and if it has type A, it looks suspiciously like it could go into F here. I mean, nobody prevents us from doing it. It's not forbidden by law, so we can just like try to call the function with the value which is the correct type, and let's see what happens. Let's also give it a name. It compiles, ship it. Well, not really, we still have that placeholder there. We might be tempted to ask what the type of FA is, but it's already here, so we give it an A and we get an F option B. And if you remember that compiler message, that it expected the function to F option of B, we can just say, like, why don't we just return that? It compiled. Awesome. So that's really all there is to it. That's the monad transformer for option. And we have written that without having actually any clue what's going on. And that's really the powerful thing about type-driven design. So just as a recap. Basically, we have these two effects stacked together here. We have something F which is unknown. It could be a future, it could be a list, it could be whatever. And then we have something option in here, and then we get F of option D back. So why is that in any way interesting? So assume you have this extremely relevant enterprise computation, which takes an n of int and then checks if factors are present. So we want to get back a list saying having a none when that specific factor at that index is present and a sum of x if not. So the implementation is really simple. We just iterate from 1 to n and check if the modulo is 0, and if yes, we give back the factor, otherwise we get back none. And if we want to compose these kinds of things, we can just use the flatmap for option function, which we just defined. So the result of that function is not really exciting. I mean, 6 is equal to 6 times 1. It's also equal to 3 times 2, 2 times 3, and stuff like that. So presumably the function output of that function is pretty clear. Now, let's say you have a business requirement of chaining these computations. So you want to go inside there and also expand these numbers here. Then you can now use our flatmap for option function. So now we have an expanded version of that, and we can kind of see the original structure still. So the original thing is still a prefix of that, and then the sum 3, none, sum 1 belongs to this, and then these two belong to this, and the rest is none, and then there's sum 1 again. And this none is there because we had an original none there. This is the first case we implemented. So if there's no actual factor present at that point, we can't factorize it further. And the funny thing is that works for stuff which are not lists. So it works for different things as well. So we were completely generic here. We have another expensive computation here. Just mentally replace task by future. Its task is the Scala set implementation of futures. And we have a function which takes an integer, and if it's 1, we have arrived the goal. And if it's even, then we divide by 2. And if it's odd, we multiply by 3 and add 1. Does anybody know what that function is called? So it's a well-known function for mathematics, and it's not really clear whether that thing terminates at all. But we can just try to compose multiple calls and for fixed length. So let's say we have that for 5 and run it, then we get 16 back because 5 times 3 plus 1 is 16. And now we can change this thing. And we can see that if we make another round, we get the 6. If we make the first one, we get the 16, and we get another round, and we can divide it by 2, and we get 8 back. And we can do that for as long as we want to. And the takeaway from that is, it doesn't matter if you have a task or a list outside, as long as you have an option inside, you get a monad transformer for free. So now here's the important question. When do monads actually transform? And the answer is, it's complicated. I can only try to give a hand-wavy idea here. And basically, what we did for the option monad transformer was, we get an input which is an option of A, and we did a case analysis on that. We did the pattern matching. And in that case, we can transform a monad. So if we know something about the underlying structure of the inner thing, then we can always do this case analysis. It's a little bit more difficult than that because, for example, for lists, a monad transformer for lists is not that straightforward. Because imagine you have a future of a list of int, and you could write a monad transformer for lists which has the correct type, but which behaves in a weird way. Why? Because all the elements in the list are being computed at the same time, they're in the same future. But what you usually want is kind of a stream where you have an element and then a future of a tail, and in this tail there's an element, a future of another tail. So basically you could say that you would have a future of every single piece of, an independent future of every single piece of data, or maybe a dependent future of any piece of data. And you can also do transforming for functions, and a lot of more things, but in general I cannot offer you any idea what like the underlying essences of that. If you are in a situation where you would want to compose monads, you should just look into ScalaIO or Haskell, look if there's a transformer for that, and if it's there, you can just use it without giving it a second thought. Since I've still got a little bit of time, I can also give you a practical example of how monad transformers look in actual code, because the thing I just showed you with these flat map for option stuff is really verbose, and you don't really want to do that. And the good thing about ScalaIO is that monad transformers can be treated as just regular monads, so you can use all the syntax you like, so you can also put it into for comprehension if you want to. So I've called this flat map proper because those things actually give you back an instance of this transformer instead of the plain thing. And the only thing you have to change for your code, you just have to call another constructor. You have to wrap that into option T, and you have to wrap this thing into another option T. And if you are inside an either or whatever, then you can just change that constructor. So apart from the simple constructor call around your code, nothing changes. And yeah, you can use regular syntax. So let's see. If you want to get the actual value back from the transformer, you have to run it. And so if you look at it like that, you can see your constructor around it, and you can remove that constructor with .run. But the important thing is, if you just take the present and now write flat map factors present and now .run. So you can see from this example, you can just use the regular flat map thing, and if you want to, you can also put that into a for comprehension. So for x from factors present 5, y out of factors present x yield y, you also get something the same thing basically. And this also works for this expensive computation we had. So we have expensive, let's say 5 T 5 flat map, expensive computation step. And now you have to run that, and you have to run it again because task also has to run a function. So you have .run. And and you get the same result. So in practical code, you would usually use these wrappers because they give you all sorts of conveniences from the regular Scala infrastructure. Okay, so wrapping up. Here's a recap. Monads are awesome, but often too powerful. As I said, using monads has some limitations. So, for example, you can't do error accumulation for validations, and that's because monads are talking about dependent pieces of data. There's another thing, because most of you know parser combinators. There's also a subset of parser combinators which are called applicative parser combinators, and they are specifically not monadic, and they can do some more things. For example, they can use optimizations on the grammar input. You can do that because with an applicative parser, all the parser elements you compose are independent, so you can do an analysis. But if you have a monadic parser combinator, the parser can depend on runtime value, so you can get a different parser depending on what your input is. You can't do any optimizations up front. Also, we learned functors compose, applicatives compose, monads do not compose in general, but specific monads do compose. And this pattern actually comes up very often in code. And once you discover that something is actually once you discover that your nested flat map, case, match, whatever thingy is actually monad transformers, you look into Scala Z and feel like that because now you're extremely powerful. And the closing slide, if you look at my badge, so Mr. T would also approve of that message. So he uses monad transformers all the time, and he's very happy that they exist. That's it. Any questions?
It's still because there was some tricky about that, but it's actually about validation no longer being monad. So I have validation from multiple things, and they're sometimes dependent, sometimes independent. So throughout my code, I use validation, and sometimes I take a sequence of code that I find, and other times the result of that then has a fence sequence on another validation.
Okay, so the question was, what if you have a sequence of validation steps where some of the steps in there can be done in parallel, like the regular validation semantics, and some of them are dependent. So, for example, this HTTP request semantic where you have fail path. So previously in Scala 7.0, you could just use validation for all of that and just flat them at one point and applicative compose at another point. The recommended way to do that in Scala 7.1 is to switch between validation and disjunctions, either our own either implementation. So validation has a method called disjunction, and disjunction has a method called validation. So if you have sequential parts, you can just convert your validation spec to disjunction, put it in the for comprehension and flat map, and then if you have again some parallel steps, you can take your disjunctions and put them back into validation. At first, it might sound a little bit boilerplatey, but the reason why you should do that is because you make it explicit what you want. Otherwise, you might have the situation that your for comprehension is not actually dependent and you're throwing away important bits of data. So by saying validate.validation or disjunction at various points in the pipeline, you make your intent clear that this point is to be treated as accumulation and this point is to be treated as fail paths. Does that answer your question? Also, we have a compatibility hack, so if you import validation.flatmap.something, you can still use flatmap, but this is going to be a way, it's just a shim. Alright, then have a good lunch.